In a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice, a flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony of science, had the potential to shift the very fabric of reality. However, a sinister force lurked in the shadows. The Einsteinian demons. These creatures thrived in the distortion of space-time, causing chaos and disruption. The world needed a hero, and Miller was ready to answer the call. With his flute in hand, Miller played a tune that echoed through the cosmos. Each note, a shot of pure ether, struck the Einsteinian demons, dispelling them back into the void. The world was saved, not by a warrior, but by a musician, a scientist, a man with a flute. Remember, in this universe of wonder and mystery, sometimes the most unlikely heroes make the biggest impact. Keep your mind open, your heart brave, and who knows, you might just find the ether within yourself. So here's to Dayton Miller, the flute ether master. His melody still resonates, a testament to the power of harmony in a chaotic world. In a world where space and time are intertwined, one man dared to challenge the status quo.
All right, sorry about that. I ran a little extended intro, but we are live now, gentlemen. Yeah, so so to start us off, if we open up our thing, I should open this ahead of time, but what's the oh man, should open that ahead of time. But anyway, if you open up any physics book, you'll have a table in the table of contents, you'll see, universal constants that they use, right? And it's like, what are these? Where did they come from? What are they used for? And, do they necessarily have to be an actual value that's associated with the physical mechanism to be used in measurements if all measurements and everything based on a model or ratios of those constants, right? Because it's always going to be in some proportional relationship in that regard. So to kind of start us off, we'll look at the electron, right? And how that's the model, the basis for, subatomic particles, for the whole model explaining, the atomic, everything that happens on the atomic and subatomic level, right? Starting with the electron. And it's like, well, how'd they get that? What does it mean? Well, they started with introducing energy into a system and making measurements with what it would take to cause that energy to deviate from being in a straight line, essentially. So when they introduce an electric and magnetic field to that system, it'll cause a deviation in that beam, and then from that, just making precise measurements and keeping it consistent with how much energy they can introduce versus how consistent they can repeat that measurement. They came up with the quantified amount that they would distribute over the radius of a sphere as the as the energy potential of that. And from that, they just made a little particle, right? And then as they build out from that constant, everything is a ratio of how many electrons are orbiting this nucleus, right? So that's how it all breaks down off of how you build off of a constant. Like the whole model and everything is built upon that. And then when they got into quantum field theory and quantum electrodynamics, when they started doing experimental verification of the accuracy of the physicality of the model that they put forward, well, they found that their predictions were off, and then they had to make new constants and adjust those and keep that going. And then that's where we got into the situation where, they just kept refining things and adjusting the constants and doing expansion series to infinity to to make everything fit this original measurement, to get it to circle back to that. So we're just kind of examine some more of these and break down the historicity of them. The big ones, of course, are the mass of the Earth and big G here, right? These are the equations that govern the cosmos. So we're going to be taking a look at those and how they all relate to, or how they're all in relation to one another, and what that means and what the implications are for just having a constant to have a baseline to jump off of, so to speak. So, all right. With that said, Shane, do you want to say anything? Do you have stuff to share for it? Okay. Oh, gotcha. Yep. Yep. No worries. No worries. I'm gonna see if I can find the table of contents for that thing, so we can get a nice list going. What we're seeing is the derivation for big G. Is that what you're supposed to? Okay. Okay. Cavendish. Not you. You said Mickelson Morley. Yeah. Measured in ball twist, I think, is the SI unit. Big G is a function of little g. I mean, there's no other way to really look at it because they need the weight of that to even begin to even pretend to do anything from it. It's the only way to do it. So so in so in doing that, right now if one were to accept that, right, like let's look at the consequences that they're putting forward, because what they've discovered, with math and physics here in the early 1800s, 1700s, right, is that you need constants to do ratios of things together. So this is like presenting the narrative to the public, right, so to speak, because like all we have are these. You can go back to the Royal Society right now and read all about the documentation of Cavendish, dude, and this whole thing like in great detail, right? But it's the importance of it is getting you to accept this as is. So it's like, okay, what did we just do here? We just established the gravitational uh, uh, force there, and then we can also, with that, we can derive the mass of the Earth now, and now we can start doing things ast- uh, for astronomical observations where we can apply our constants and ratios to see if those match and then those will of course match the periodicity because that's all it's ever been a function of. But this is how they slid everything in, getting you to accept this, because when you do like energy analysis and stuff, you you need some constants to go off of, something, like even if it's not true, it still has to be some value in there. And this is just like the story that they've put forward is like, oh, we just happened to measure the Earth, dude. We measured the weight of it. We measured how much that gravitational force is. Ah, the one trick they never tell you about. Hey, what's up, Piezo? Nice. You got some time tonight? Because we want to talk about the ether density thing you showed us earlier. That was awesome. Nice. Just to grease the axle. No, man. No. Xavier, did you need anything else on that? Cool. So yeah, let's get into the deriving the AU, because this is all going to be a function of how everything scales, and everything has to be proportional. Like we talk about scale invariance a lot and proportionality for periodicity. Well, this is going to be how they derive this from optics, from using constants in optics.
We're gonna figure this out based on a known ratio of something we're gonna totally make up and assume right now. Oh, it's like in math, right? When you're using ratios and measurements, you're like, oh, I can do that if I know it's a known ratio. And for this known ratio, someone took a guess. They were like, yeah, it's probably about right. And then later, with backwards compatible math, they were like, oh, you know what? You were exactly correct. It's 1.00. Anyway, moving on to this math over here, we have continuation. This is actually the square root of 3 times the square root of 2 times the constant equaling this. So we have the orbital periods of Earth and Venus, just getting Earth, just using Kepler's third law. We can estimate the AU distance, which is, of course, the distance from the Earth to the sun, which they're going to use and compute as 1 AU to mark and delimitate distances going forward. But it is the Earth-Sun distance. It just uses orbital periods and distances. So they use that ratio, they compute it, they get, well, 0.99 astronomical units. But that's just with this ratio. So they would just assume that, and they would know exactly, oh, if you actually do the conversion to meters, it gets to 93 million miles is what it comes down to. Now that's not that's not what they claim to have done, right? This is what they claim to have done. They claim to have used the solar parallax angle. Now, again, if you haven't looked into solar or parallax at all, Alan's got a wonderful presentation on it. We have a list on it. It is absurdly small angles that they're dealing with, first of all, to do anything and then make inferences of. Plus, in the case of reality, stellar parallax goes, 46% in the other direction. So if you're using it to imply Earth's motion, Earth's moving halfway in both directions at once or whatever. So that's a little bit different. But if we're going to use they said that they use parallax to compute the distance to the sun. So someone took an angle of a star and went, ooh, that tells me in miles how far away the sun is. No joke. This is real history, guys. Let's just put a disclaimer. This is what heliocentrists actually believe. Okay. So we do a little bit of math. We just get an angle. We'll call it, this one, we'll do the angle in degrees conversion to radians to get our actual starting measurement. So the next slide is where it continues. This one. It's funny, right? Because what Alan said about converting it back to optics means that this doesn't work. None of this works without the radius of the Earth. You can't have it without the radius of the Earth, right? And we know the radius of the Earth is derived from optics based on angular resolution limits and distance to the horizon, based on regular wavelengths and a 6-foot observer. But that's, again, a different presentation. We'll get back to that. But just know that this doesn't go forward without this value. So they use parallax distance measurements. They assume the radius of this. They plug in the radius. They use the proportionality of Kepler's third law again to work out the math to calculate to yield. Oh, look, actually, it turns out it's right where we found it, 93 million miles, just where we assumed it. And the other part of that is the people of history. There we go. The people throughout history, right, who had guessed at the distance to the sun was just manipulating a optical diameter formula. Remember when we always say, angular size formula? In fact, Red's Rhetoric, our boy, shouted this formula out at me in anger over some unrelated things about Polaris. But I guess he wanted everyone to know that he knew it. And to be fair, it's a good formula, right? We scooped it up immediately. Thanks, Red. Now we know exactly what all this meant, right? When Copernicus estimated the sun was 3 million miles away, it's like, well, how did he do that? Well, if you assume that the sun is 0.53 degrees, meaning that it appears to be just about, if you put your thumb on it, it's about that big. It's a measurement of the optical diameter of the solar disk, right? That's what that is. If you assume that it's, say 322,000 miles away, then it's, 3 million miles wide. He's assuming it's a huge sun and it's 322,000 miles away. All of these would work for this apparent 0.53 degrees. So by manipulating this formula, right, you can see that you got this. Now, by the end of this, you get really, really close in 95, 104. But the only thing that's changing in this is the manipulation of the distance and the diameter, because we know the optical disk doesn't change, but actual size of the sun, diameter in miles, and the distance to the sun in miles. Those are the two components that are being manipulated in this formula for D over 2 times D, right? Because you got the little d distance to the sun, big D with the diameter of the sun in this case, right? So these people are manipulating a backwards engineered constant to say, oh, look, we know for sure based on stellar parallax angles and not based on this formula at all that the sun is 93 million miles away. And if you look, I did all the calculations here.
When you get a chance, though, swap up the headings of columns 2 and 3.
Yeah. Right. Distance and diameter for sure. This would definitely be the distance and this is the diameter. But essentially, it's all just these people, this meme, right? People are like, oh, we were only getting more accurate. And it's like, well, that's not true either. But the other part is you're just manipulating what you think the distance to the sun could be based on the diameter, right? And once you get one right, it shifts proportionally. So that's the other portion of the constants. And I think we have Planck's constants to go into if you want a little bit. And then Piezo gave us the metric to determining the density of the etheric background.
Dude, well, Piezo's AFK. So, does anyone have any questions about what we just went over so far? Or any thoughts?
Yeah, how do they determine the diameter of the sun? I was paying attention, maybe I didn't understand.
Oh, right here, and they make wild guesses until it works. Yeah. Yeah. Because of the covariant scaling factor, they know that this is the true observation of the sun size. So the other two fucking willy-nilly play around with, doesn't matter. Like, so you just find the proportionate covariant scaling pair that matches with this, and wouldn't you know, this is where it gets 93 million miles and 864,000 kilometers wide, happens to fit perfectly or something, right?
So you assume one to get the other? Is that basically it?
Yep.
Yeah, so
this
remember,
relationship.
Yeah, so remember they had a distance already, from Kepler's laws from the astronomical unit. So now the task was just to make the the apparent size, you see the angular size match the, a distance proportional that would give you the actual, quote unquote diameter of the sun, right? So that's where that's how it's all derived.
Got it. All right, thank you.
Or what they assume to be the actual diameter, but it just fits with the periodicity, right? So then, they further built upon that. That's why when it got to Arago, Aries failure, Michelson-Morley, that's why those things were so significant, because these constants that they had built their worldview on, that they had built their model, their cosmological model on, were being tested, and they were false. But yet their math still described things. So it's like, obviously the things were happening independent of their math, and they were just refining the math to meet the observation. But look at all in between that period of time, look at all the power and virtue that they harvested over, progressing science and figuring out, based on the mass of the earth and all this stuff, that, it was just too much to let go. Like, once you have that, like, how are you going to give it up, right?
Can you not abuse it to control the whole world and manipulate the minds of millions? Of course you would.
Just
I
keep
guess.
using hot glue on the house of cards.
Yeah.
What about planks? What about the planks?
And then
Complaints.
keep in mind this this scale only applies to like the solar system as we see it, right? They where they get into things like the Hubble constant, the cold dark, or what is it, the lambda, the cold dark matter model, and all that stuff. That's where, after the fact, when they had different optics and they started discovering that there's more things in the sky emitting energy, and to explain that and fit it within their model, that started to fail, and they had to introduce new constants to explain things. Like that's where all that stuff comes from. It's not like they figured out that the mass of they figured out the missing mass of the universe. That's what it had to be to fill it in observationally, to keep everything else proportional and to keep it together. I mean, we're reading that book, about the redshift observations and, directly related to Hubble's constant and all that, and the belief and adherence to all associated with all that. And it's like, that's just based off some dude's interpretation, and Halton dared to have a different interpretation, and they were like, how dare you, and took away everything from that man.
How dare you?
How
Yeah, I'm
dare
still
you to-
skeptical that you can determine the mass of something through looking at it.
Are you sure, man? Did you drink enough Kool-Aid? Let me get you a robe, because that's definitely how we determine masses of all stellar objects. Always how we know. In fact, during my eclipse deep dive, if you look in Stellarium and you watch, say, an eclipse cycle, you'll see in the lower left-hand corner, if you're focused on the moon by hitting it or doing this query or whatever, it'll give you the data stream, and its mass is constantly fluctuating. And you're like, why? Why would its mass be constantly fluctuating? And it's like, oh, because the optical diameter is constantly fluctuating as it gets more or less obscured. And that's the most retarded thing that I've ever heard.
Oh yeah.
All right. Mass fluctuation. Oh, nice. Historically has been problematic. Let's just say. The trick is, it's like, hey, how do I give you? I'm going to tell you the mass of that thing in the sky. You'll never in a million lifetimes be able to confirm any aspect of this, nor will any of your descendants in living memory or history. But I'm going to tell you with a level of confidence that I know what that star weighs. That's a brilliant move. It's like, okay, cool, Chief, cool story, right?
It's inherent in everything in their mindset. It's like just today I heard on the news they were talking about a 1,000-year storm. And I'm like, okay, so you have weather that tracks back, maybe 700 years, weather tracking. Even if you could go back 1,000 years, that's not enough data to claim 1,000-year storm, like 1,000-year flooding or whatever. Like it just, the assertions inherent in everything in our everyday lives is really insane, especially once you start considering the fact that once you make one assertion like that, and then you start making other assertions alongside them, and you combine those assertions to then make draw conclusions about things based on, like, you have multiple margins of failure built into your equations, and then those are compounded within your results, your result set. So which would essentially be your model of the universe in this case. And so, or with the case of what Shane's talking about. So it's just essentially, when you're asserting all these things that are just guesses, and you have all these like variables that you're just kind of filling in with a best guess, you're completely into, what we would call fan fiction or lore. You're just making things up. It's just all a big fun story that, you're insanely precise, but it's just a bunch of false precision because it's precision about, or you can call it real precision about your fantasy land or whatever.
Consistent precision about a fantasy land. Yeah, you're consistently accurate at describing the contour of Superman's under ruse, right? But does that mean that Superman's flying across the sky? I can always guess with calculus the rate at which the area under that butt curve, but does that mean that he's flying? No, it doesn't. Anyway, this isn't strictly related, but I wanted to throw it in there as the meter. What do you think, Alan?
Oh, absolutely, man.
The meter.
This goes right in tandem with once you have something established and you make a system, a unit of measurement as a ratio of that established system, well, everything's going to work in it accordingly. So yeah, it's directly related, really.
It's crazy. It's crazy because they think this is one of the biggest ways they got us. They're like, ha, go measure the world in any metric unit known to man. It's just units of a sphere, guys. It's like, ah, we got you. That's a tough one, right? Because people are like, no, they changed it, and it's like they changed nothing. They changed the historical contextualization of what they'd already done. That's all that changed. Everything is the same. It's exactly the same. As a matter of fact, let's see. Let's go to the other one. This one. Just because. Like just because they say they ratioed it against a different thing, in this case the speed of light, and of course maintained by the constancy of the oscillation of cesium, doesn't mean that the actual value of the metric changed in the first place. It literally went from 39.37 inches to 39.37 inches to 39.37 inches, and they're like, nah, we changed it. And you're like, but changed it to what? And they're like, well, it just says that it's a ratio of it, and it's like, shut up. It's exactly the same thing. It's always been a proportion, a 1/10 millionth of a terrestrial meridian, meaning a meridian, of course, guys, meaning a bisecting great meridian means you have a sphere. If you have a meridian of anything, it's a sphere. If you have a bisecting meridian, it's a sphere. So a meridian, a terrestrial meridian, means a land sphere. Okay, so we're starting off with a definition of a land sphere, and we're trying to get the dimensions of it. And then we're like, oh, you know what's best to measure dimensions of a land sphere? Well, proportionate ratioed units of a land sphere. So that's how they started. From the North Pole to the equator, they have ratioed that as a proportion of a meter. And then if you tell that to Globers, they're like, well, that sounds uncomfortable. I don't like the way that is. That's not what it is anymore, silly. Now it's ratioed against light speed. And again, same value. They just found a different threshold to ratio it against to make you think, though, now it's safe. Now it's a meter. And of course, a meter is used to get what? You get inches, inches to miles. That's 2.54 centimeters to an inch. You got meters to kilometers. Then you get kilometers to miles, right? And then you get statute miles to nautical miles, which is 1.12 something like that. So all of it, right, is just ratioed to a meter. You're only counting things in various forms of a meter. And then if a meter is a portion of a terrestrial meridians, we're just counting things in little baby terrestrial meridian. Right? And then they're like, oh, how come the distances always add up to a big terrestrial meridian? And you're like, well, I don't know. I got all these baby terrestrial meridians laying around, and I put them together to make a line. And then now it's a big daddy terrestrial meridian. Like, I don't know how it happened. But that's why I say all the distances are globe distances, right? But
Little baby terrestrial meridians.
Widow to West Wheel Meridian.
and then it's like, that's not a problem. And well, I mean, it is a huge problem, right? That's why I had to put the first slide in there, because I was like, Flat GPT, explain as if to a child why measuring things in units of a sphere is tough to prove sphericity. Right? Like, if this is the measure, then how do we differentiate? And literally it's like, okay, well, here, like, everything is in spherical coordinates, first of all, as I always say, longitude, latitude, and compared to the celestial sphere. So anything you point to, you're going to use that. But the main kicker is any distance measured in meters can directly be related to the spherical geometry of Earth. So, I mean, how come it always equals a sphere? Well, I have an inkling, right? And back to this one, right? So, yeah. What do you guys think about the meter and the terrestrial meridian?
Pretty fun, pretty crazy. Well, now it's also tied to the speed of light since like the 80s. So it's even more. The meter is wound up in all sorts of fun derivation at this point.
I mean, not really derivation. They just took, hey, what proportion over this would still equal the 39.37 inches that I know it has to be? And they gave us that. And they were like, look, now it's ratioed against the speed of light. And they're like, well, how many terrestrial meridians equals 1/299,790,158? Oh, one. Okay, cool.
Nice and clean.
Like, that's the relationship. That's why I say, like, when they say they now ratioed against the speed of light, all they did was change the historical contextualization of the first ratio.
Which means that a meter is longer from
East to west, north to south. Yes, sir.
Yeah.
Yeah. If they tied it, if they kept it to a terrestrial meridian, that wouldn't be the case, right? But wait, it's both. That's hilarious.
This is absurd.
It's absurd. Do we want to get to the big gravy, or do we want to let Piezo describe it?
I think he's still AFK. I was looking for, the story we're told about Eratosthenes, where what did he do? Oh yeah. So the stadia, right? They're like, oh, Eratosthenes, estimated he was pretty close to getting the circumference of the Earth. And it's like, well, how'd they do that? Well, nobody knows what a stadia is, but a bunch of lads got together and agreed that a stadia would be a ratio of a terrestrial meridian. And oh my God, they just
No way.
so when they say that Eratosthenes guessed within 98% of accuracy, all that is that some dudes literally just picked a number that gave them 98% and was like, that's what a stadia is.
Yep.
That's all it took.
That's how ratios work.
It's not like there's a historic record of like, oh yeah, dude, these guys figured out a stadia. They had a different system, but when you convert, no. They just agreed it's this system and imposed it on history.
This is how many baby terrestrial meridians we're going to count it towards. I'm just going to start calling meters baby terrestrial meridians.
That's there's no other way to really call it anything else now.
It's like, hey, how many baby terrestrial meridians is the equator on your flat Earth? It's like, well, it's kind of a loaded question. Oh, dude spent 3 hours asking me that today. I made him a meme. I wrote him a rap song, gave him a music video. I did a little anime. I did a GIF, wrote him in text, sent him a dude. He asked the same all day. But how long is the equator on flat Earth? I'm like, good. Well, 2 pi r based on the graticule, meaning that you get what? 2 times the radius would be 3959, be 2 times pi 3.14 times 3959 would give you 24,901, which would be statute of miles away the circumference if you're doing optically, right? But that's just according to the graticule. And he doesn't take that, right? He just makes me say it over and over and over again. And then at the end, he's just like, sphere. It's like, but I addressed this immediately. Anyway.
Yeah, I think Pizio might be gone for the night. I think he said he was only stopping by real quick for something.
Cool. You want to wing it then?
Let's see here. I mean, by you want to wing it. I'll trust fall into you doing it. Then yes, I'm definitely okay with that.
Cool. Stone, have you seen this yet?
Nope.
So we have essentially, to our judgment, gauge the density of the etheric background. Right? And this is just pretty much the density of the medium, any medium, based on energy in a wave formula. Right? So this dastardly thing right here is what we're manipulating to shoot the density of wave propagation in the medium. And this would be a medium. Of course, we're saying the medium is the ether. So you got energy in joules, mass per unit length, wave speed, time, frequency, amplitude.
Okay. Back up to mu. Mass of what per unit length?
Per unit length in kilograms per meter.
That's supposed
No?
Mass of what per unit length?
Was it tied to the Planck? Just says the mass, right? VT.
Yeah, the mass.
The mass.
Mass of what again?
That was supposed to be the density of the medium.
Is it?
Yeah, so this was some wave equation for energy for whatever
You're actually talking about the density of lines of force coming at us because of the ether? Is that it? Because there's no mass involved.
No.
It's an electromagnetic force. It's not this is a misperception, as far as I can see so far.
Shoot.
See, we're
Oh, it's a
talking about
bummer
the
we don't have piezo.
frequency
Let me
and
try
amplitude
and. Did anyone
of
try
a
pinging piezo in
wave,
chat?
Yeah, I tried.
but this is paradoxical to assume that that wave has mass when it's transmitting through the medium of some other thing like, physical space.
Well, the other one didn't have mass, Alan.
Well, it's not the mass of the wave. It was supposed to be
Yeah.
the mass of it's a density equation for I'm sorry, it's the energy equation for a wave propagating through a medium, and like how much energy it would have based on those variables, right? But if you reverse it, where you know the speed of light and you know the time and the hertz and the frequency and all that, then it would give you would be able to solve for mu. I don't know why I like wrote it messed up or whatever, but it's supposed to represent the medium that it's propagating through to give you the direct energy proportion, like how fast it can propagate through that medium.
Because we're just trying to find mass per volume, essentially density, right? So we need mass to start. What do we do here? Let's see. Mass. There's no mass here.
That's what I figured.
Yeah. Yeah. So I don't know what happened there. So I bet.
Just
I was like,
checking.
there's no mass in the one that actually computed, dude. that I can recall. Oh, let's see.
No, it gives you the average density to allow electromagnetic propagation to maintain that frequency and speed.
Yep.
Is all. But I'm not sure where all the math got lost in translation or whatever, but that's what it's supposed to represent. They use
That
it for
happens a
other
lot when
stuff.
people start to juggle formulae.
Yes. Little formula jugulation.
I think this is directly from Piezo's homework, and he came in and was like, "Hey guys, guess what I have?" And we were like, "What? What is that? Let me see that."
Get down the path, Mr. White Bunny Rabbit.
Yeah, the calculation for, and like essentially looking for, if it's all pressure mediation and density, then you're looking for like what, pounds per what, kilojoules per square kilogram or something, dispensation against density, which would be directly proportional to mass, which would be what, measurement of literally the grip of ether torsion on the world or whatever, electrostatics. So the mass per unit length of the ether, mu, is 2.2 times 10 to the negative 30. That's a pretty small number.
Yeah.
Yeah. Well, we were looking at Otsutovsky's numbers too, and being like, his are really small too.
Yeah, he's got some tiny numbers.
Yeah. Hugely, like infinitesimal.
No, I would just call it a misperception and misattribution.
But he's defining
Until
it.
you can, I don't know, man. Until you can pin it on a tangible, you can't use tangible units to measure it like that. I'm kind of sounding rhetorical, but I would refer you back to how things went last night regarding the ether.
Word.
That it's a result. It is not an entity.
An entity. That's true. But like, as a tenuity rating of a background medium, it would have to have a value of some sort, which you should.
It has attributes. Yeah, anything has properties, but physical presence is not a measurable aspect of it.
Because I don't even know what this is. -8 times 8.5 times 10 to the negative 12. That's the density.
Yeah, it's a negative density, just shy of nothing. It's just negative nothing, but only a teeny bit negative.
Just
right?
shy of nothing.
Well, even in scientific notation, this number shouldn't be negative to my mind when we're doing.
It's just a hair's width, even less than nothing.
We're measuring a fly on a hare's ass, but it's too big.
8 billionths of a kilometer per cubic meter of next to nothing because it's slightly less than that. which
So
would be
what instrument do you use to register 8 millionths of a nothing? By the way,
That is a good question. Ether density. Yeah.
yeah, an ether
That's a
density
great
gauge.
tool. What is the tool?
It must just be calculated. You can't actually measure it.
I mean, what do I order at Amazon that measures things in kilometers per cubic meter? And is there an Arduino module of it? Okay, I'm going to be back in about a minute and a half. One sec.
Word.
Were there any other constants in nature? I think those Planck's constants, but those are just derivatives of the other constant, so nothing special. It's like once they have the basics, they can continue to make up all the other shit, right? Planck length, Planck time, Planck energy, Planck mass. It's just like, oh, well, Planck length, combination of the other constants, combination of the Planck constant, gravitational constant, let's be like. So different algebraic expressions there, different cubes, different functions, different curvature functions, but same thing. And then you just reinterpret it to be like, well, it actually represents the length of this, not necessarily a mass scale nonsense particle or whatever. So constants have value, and they've corrupted that value to support their nonsense physics, and that's what they needed, right? They've retconned the world to get real life constants, to get things that aren't real to be substantiated, right? Mass and stellar objects get substantiated by big G, which is crazy. It's a derivation of little g and the torsion of two masses on Earth. And they're like, oh, you know what that means? How much that star weighs. 1-for-1 direct correlation.
When you say it like that, it's...
Trying to make it sound as logical as I can, but it's ridiculous. Well, that's pretty much it, man. That's a lot of math. A lot of math for tonight.
Who or what helped them figure out how the fuck to do that?
Right?
Good question, Alan.
What's that?
I'll pretend to throw his voice down there by levelist.
What's up? What'd you say?
I practice ventriloquism.
That's really good.
Does he have two mics hooked up? How does he do that?
So do we pick a topic that nobody gives a shit about, or nobody has any questions? Contents are kind of important. They built all the physics around them.
Pretty much sums it up.
Yeah, there was that awesome video that Toby linked earlier. Do you think, can we watch that to play it out, or?
Yeah.
Ooh, that would be
Yeah.
kind of cool. That video is pretty good.
Yeah, that was awesome.
Yeah, let's watch that to play it out. That sounds great. Are you in Windows, Alan? Should I boot up?
I can do it.
Shane, we can make Shane do it.
Nice.
I need both of you to sign an affidavit that Windows is superior in this instance.
Nah, I got
I
Ballard.
can't do it.
All right, you shoot me the link.
An affidavit, huh? Jesus.
Yeah, man.
Are you guys using Linux, I guess?
Are you talking
Yeah.
about the superior OS, except for this instance in particular?
Does PC master race only apply to Windows PC or what?
Bro, I'm a Windows dude all day long.
All right, I'm back.
Welcome back, Stone.
Yo, we were just about to watch a video to roll to essentially play things out here about Planck's constant and universal constants.
Planck's constant. Sigma t to the fourth is black body radiation constant?
Yes.
Yeah, actually.
Bitchin'.
Shout out to your boy Planck and his constants.
Your homeboy playing.
Young Plank, they called him back in the day.
I think you went by Plankton to his boys.
I think that was like a nickname.
Only if you
he
knew
had.
him, though.
Right.
Yeah, it was on the download of the G's.
I think-
Something tells me this is part of the formulation of just exactly how they got to the figure for absolute zero in Kelvin.
One of the first gangsters.
We do like to follow those hunches.
Not to spoil it.
Morley's running some updates on his Discord.
Nice.
Give me just a second.
Oh, Shane said he would do it.
Yeah, I got it.
Oh, nice.
I was only kidding about the affidavit. I just need to sign email in blood if you could do that.
Had Discord and like YouTube and shit. That'd be crazy.
I was waiting to download it because it looks chunky. There we go.
Oh, what up, Morley?
How you been, Moore? Been out there measuring?
Who's Morley?
Mickelson's lab assistant, Miller's lab assistant,
Oh,
otherwise known as a true homie, a fellow periodicity measurer.
All right, there we go. I think I'm good. Streams up for me. Streams up for my stream.
I'm in there.
A little quick 8-minute, 10-minute, 12-minute, 13-minute video. Maybe we should put it up on speed. Now we can't.
Nah, just play it.
Good? Everyone in? All right.
In a computer, the information you would need to enter is first.
I think you gotta slide it back a little bit.
Oh?
Yeah, it started.
If you wanted to simulate the universe in
There
a
you go.
computer, the information you would need to enter is first all the laws of physics, the initial conditions of the universe, and about 20.
Did you just say you just got to put in all the Planck's constants?
He's
G constant, the big constant, and then you're good,
Oh
right?
yeah, this guy says some hilarious stuff in this video. But
Okay.
Oh, you mean you want to simulate the astronomical universe? Because if you want to simulate the universe, you need the opinions of absolutely everybody who ever lived, and then you need to get the birth records, and then you need to find
Yeah, that's a crazy thing.
DMVs all over the universe, and then there's university records for all over the universe. Got to put those in there, and then there's the news headlines for the entire history of the universe. You get those too, and put those into your computer, and then now you've got some simulation going.
Off to a great start. 9 seconds in. Everyone disagrees. Here we go.
And it all started with a little assumption.
These constants are
Just one assumption, guys, and then 10 million more on top of that one.
needed
came
in
from
order to
nothing,
describe
go.
the universe as best we know it. And if you did this and let the program run, you would end up with a universe which would pretty much look identical to what you see all around you. We're familiar with the laws of physics, but what are these 26 fundamental constants? These are constants that have to be measured and are what they are. There is no current theoretical basis to predict what these should be. The first
Whoa, I didn't know that.
the rest masses
Oh.
of the fundamental particles.
Dude, they got me again. I just assumed this stupid model had a theory, and they just like, nah, we're winging it, bro. We've been winging it. We wing it still.
yeah, this guy's pretty good because he's pretty candid about everything.
Dude, no theory. Like, literally, we have no freaking idea, but here's what it is. It is what it is.
What do you think he meant by no fundamental basis?
Of the standard model. 6 quarks, 6 leptons, and 3 bosons. 4 of these numbers are the quark mixing parameters. These are required to describe the weak nuclear force and nuclear decay. Another 4 numbers are the neutrino mixing parameters. These describe how neutrinos mix with each other. There's the cosmological constant, which describes the amount of acceleration present in the universe's expansion. The fine structure constant, which represents the strength of the electromagnetic interaction. And finally, the strong coupling constant, which defines the strength of the strong nuclear force involved in keeping neutrons and protons glued together in the nuclei of atoms. But you'll notice that these constants all apply to some kind of object in the universe and how these objects interact with each other. They do not apply to all things everywhere. So perhaps they're not so fundamental in that sense. There are, however, 4 special constants that apply to everything everywhere. So these may be the most important numbers in the universe. And what these constants reveal about the universe is rather astonishing. What are these special constants, and what do they tell us about the universe in which we live? That's coming up right now. Before we get into the incredible story of the constants of the universe, let me tell you part of my inspiration for making this video. I watched an 8-episode series on Magellan TV, today's sponsor, called The Secrets of the Universe. This series looks at some of the strangest phenomena in the universe using some superb graphics and supercomputer simulations. Magellan is a new kind of streaming documentary service founded by filmmakers and producers who bring you the best documentary content. Featured subjects include history, nature, technology, and of course science. You can watch it on any of your devices, and if you enjoy 4K, you're going to love the library. Magellan has a special
nothing
offer
compared
for
to
all
libs
the
of
Astros.
TikTok.
If you click the link in the description, you'll get a free 1-month trial. If you want to support
Sounds
the
like
channel,
digital propaganda on demand or whatever for a nominal fee.
link in the description. Consider the simplest atom, the hydrogen atom. It consists of 1 electron and 1 proton. To describe its interactions, at a minimum, you have to know a few of its properties. These would be properties such as the fundamental charge of the electron, the charge of the proton, the mass of the electron, the mass of the proton.
How about where it
and the
is?
strength of the
Nope,
electron.
not necessary. Don't
These
need
can
that.
be found from the fundamental constants. Fundamental constants means they
How
are
about its
measured
location?
properties because we do not
Look about all the stuff we can infer without ever actually knowing where it is.
exactly what these numbers would be.
Little
so
bugger.
These cannot be derived. They have to be measured. This is not to say that some mathematical model doesn't exist which could predict these numbers, but it does say that we currently do not know what such a theoretical model is. It is possible that a future theory of everything, perhaps something like string theory,
Oh yeah,
predict
that'll
these
that'll
numbers.
probably do it.
Now, if we go back to the same hydrogen atom model, in order to model its behavior even more precisely, we would have to take a few other fundamental constants into account. The electron and proton, for example, have rest mass. Therefore, they would gravitationally attract each other proportional to the gravitational constant g. This gravitational constant appears in both Newtonian gravity and general relativity. It can be thought of as the proportionality factor between the strength of gravity and the masses creating that gravity. Since gravity applies to everything everywhere, g is the first of 4 constants that is universal. It has units of length cubed divided by mass times time squared. The electron and proton would attract each
There
other
you go.
proportional to the permittivity.
That's the equation we just had, but you
Yep.
can't get mass without little g anyway.
Perfectly relative to
Yep, yep, yep.
what you guys were showing earlier. Yeah.
Of free space, epsilon naught, because this permittivity is the electric constant based on James Clerk Maxwell's equation.
This is going to be light speed, right? The light speed based on the properties of the vacuum.
Yep.
And
Yep,
since
give or
the
take some
electron
medium
is
density, for
spinning,
sure.
It would have a magnetic moment proportional to the permeability of free space, mu naught, because it is the magnetic constant, also according to Maxwell's equations. Mu naught and epsilon naught are properties of space and are constants that have to be measured. There's no theory that predicts their values. Turns out that mu naught and epsilon naught determine the maximum speed of light in the universe. This was found by James Clerk Maxwell as well. The speed of light is a very interesting constant. One way to think of it is as a conversion factor between mass and energy, as found by Albert Einstein in his famous equation E equals mc squared.
That's a terrible way to think about it. Nobody think about it like that.
Factor between the time dimension and the 3 spatial dimensions of our 4-dimensional universe. C also applies to everything everywhere and is the second of 4 universal constant. It has units of distance over time. Another constant which applies to everything is h, Planck's constant. It is the fundamental constant that sets the minimum scale of quantum phenomena. It can be found in just about any quantum mechanics equations, from Schrödinger's equation to the QED Lagrangian to the Dirac equation. It is associated with quantum states and transitions of quantum states. Planck's constant has units of mass times distance squared divided by time. Finally, there is Boltzmann's constant, which also applies to everything. It plays a role in determining the amount of vibrational energy contained in an atom related to temperature. It is just the definition of the energy contained in 1 degree Kelvin. It is in units of energy per degree. And using just 3 of the 4 constants, G, C, and H, we get some extraordinary insights into the nature of the universe. So for example, if we take these 3 constants and manipulate them mathematically like this.
Hey, where'd that mask go, Meow?
Wait, globe, it's a globe. Hold on.
We get a length.
If we
What
just
is this?
algebra the
Well,
shit out of
this is
this,
the
all we
Planck
get
length.
left is length.
It is the
Every
minimum
time.
length that
All
would
right,
be
so look,
meaningful
pause
for
real
quantum
quick.
mechanics.
We started with we started with the constant from Big G from Cabin Fish, right? And then we have H from how much energy can exist over 1 second for Planck's constant. You don't have to rewind. I was just gonna.
Oh, I got it, dude. I got it.
Oh, you're good. Well, now
H is Planck.
now I lost track of what I was talking about though.
I'm too good at it. Come on, man.
Yeah. So anyway, just based off of those, right? They've now they're going to tell you all the stuff about the universe. Anyway, continue. Over the speed of light squared or cubed. Sorry.
Crossing out of stuff again. I really liked when he crossed out stuff and reduced.
Yeah, can we
Yeah,
watch
like that
mass
mass.
can we watch that mass distribution real quick?
Yeah.
Boom, ready?
So, and keep
Boom.
in mind,
Hold on.
so what I was showing earlier with the electron, right? When they were doing that experiment to get how much deviation they would get off the center, that's how they extrapolated how much mass would be needed when they ratioed it over, when they ratioed that energy over the radius of a sphere. Like with that assumed amount, then they could go, oh, okay, it must have weighed this much then to produce that deviation. So that's where they put mass into it. Like they've never weighed an electron or anything,
Yep.
right? They bring it in when it's convenient to make the prediction for the deflection, and then they take it out when they when they don't
When it
they don't
becomes
need it.
inconvenient. Yeah.
Well, they can always squeeze something in and then square it a few times to
Oh, you know what? I found Shane's constant, and when added to Alan's constant, that fixes all the problems. Actually. Oh, and we need another. Oh, you know what? There's a Toby constant, and we need that one too, and that fixes the new problem.
I'll get a constant one day.
Yeah.
Seeing how many things are assumed. Oh, god. I think Flav.
Well, this is the Planck length. It is the minimum length that would be meaningful in quantum mechanics. Similarly, by manipulating these constants mathematically,
Would the mask go meow? Oh.
we get time. What is this time? This is the Planck time. This is the minimum time that can exist that would be meaningful in quantum physics. We can also get energy by rearranging.
It's kind of
some
like
these
hammer
constants.
time.
Nice.
What time? Hammer time. I get
Planck
it.
energy.
But different.
This is the maximum energy that could be contained in a cube that had the size of 1 Planck length. We can convert this Planck energy into mass by using Einstein's famous equation, E = mc squared. This represents the maximum mass that a cube of 1 Planck length could have. All these are values for the Planck scale. This scale really applies to everything in the universe. The units of these scales may be the most natural units for measuring things. Since these numbers are ubiquitous in physics, physicists often just use what's called natural units and set these three constants equal to 1. But
There it
what is
is.
the significance
There's
of
the
Planck scale?
integerization.
The Planck
Boom.
length is the shortest
Integerization
length
of
that anything in the
physics.
equations of quantum mechanics. This is not to say that something smaller doesn't exist. For example, the singularity at the center of a black hole is supposed to be an infinitely small point with infinite mass density, but Planck length is the smallest unit that we can measure. It is the smallest scale that we can theoretically probe with particle accelerators. These scales are the theoretical limit, but in fact, it is many orders of magnitude smaller than what we can practically measure today with the most powerful accelerators like the Large Hadron Collider. The Planck length is fundamental. So for example, if string theory is true, then the strings would presumably be as small as the Planck length, any smaller, and they could not be defined in physics. This would also be the smallest size of the loops in loop quantum gravity. And these strings would vibrate at minimum time
10 to
scales
the
of Planck
negative
time.
99,
In loop
because
quantum
our
gravity,
calculator
the
won't
movement
go
of the
any
spin
smaller
network
than that.
Without it saying boobs or whatever.
Increments of Planck time. Planck time is the time it takes for light to travel 1 Planck length. It is the smallest measurement of time that has any meaning in quantum mechanics. Planck time is the closest time to the beginning of the universe, occurring right after the Big Bang, that we could theoretically model.
Did you guys like how it also supports all our other bullshit theories without substantiation simultaneously or whatever?
Separated out and became a distinct force from the other three. We have no idea what occurred prior to this time, nor do we have any model for what could have occurred. Using the word before may in fact be meaningless because time itself started at this point.
It's about here-ish.
Even though we have no model for what occurred or what may exist
I love
on
a good
scales smaller than the
paradox.
Planck scale, many people, including scientists, speculate what that could be. For example, it could be a kind of quantum foam where gravity could fluctuate or be in superposition. Perhaps this is where gravity and quantum mechanics unite somehow. Or it is possible
Just don't say ether.
that space-time itself is quantized at this level.
Oh, good. Quantized space-time. That's much better.
Space-time be in superposition like other quantum
Need more
phenomena?
discontinuous dots and
Perhaps,
flux.
but this would violate the current understanding of gravity. Quantization of space-time at these scales is the kind of universe that the theory of loop quantum gravity implies. What about Planck energy? If the Planck energy was confined to the volume of a cube the size of one Planck length, it would form a black hole. The Planck mass is considered the smallest possible mass that a black hole could have. If we could
What a neat metric to know for absolute certainty, huh?
It would have gravitational effects at the quantum scale, and we could perhaps crack the holy grail of physics by understanding how gravity works at quantum scales, and finally come up with a theory of quantum gravity. If we actually built an accelerator that achieved the Planck energy for a particle like
This
an
is
electron,
nothing
a black
more
hole
than
would form.
nerd
So it would not have to
porn.
go to higher energies
Yeah,
than that,
at this
because
point.
the
But
black
the first
hole
part
would
was
just be
good.
bigger, and there would be no information that we could attain. This is why the Planck
Well,
length is the smallest length scale.
Like
that
Toby
we
was
could
saying
theoretically
though,
probe.
it gets into that
Note
fan
that Planck
fiction, right? Because
energy
once you got these
converted to
constants, I
Planck
mean,
mass is
like
really
George
a
W.
lot of
Bush
mass
Sr.
packed
said,
into a very
don't let
small
a good
space.
constant go
This
to
is why
waste.
black holes form. The mass is
That's a direct quote. Yeah.
So like why stop there when you could establish the smallest units possible? I mean, think about it too, because these people have established their philosophy on getting there first, right? So they got to establish the smallest amount of energy, the smallest amount of distance, time, etc., and go from there to cover it.
Why is this the case? You have to remember.
And once you're like, look, we've done it, we've measured the smallest amount of anything, you're like, oh, see how the smallest amount of anything also applies to my crazy fictitious string theory world where everything's made of bubbles. It also applies to my Lego world where everything's made of Legos. This is the smallest Lego you can now have. And it also applies to my galaxy string theory button window where everything's a button, right? That's the smallest button you can have. And it's like, oh, that just, you stacked up a bunch of nothing on more nothing and it just farted. Like, okay, cool. Great.
Here, we rewind it a little bit and play it back because I was kind of talking over it.
In fact, scale that we could theoretically probe. Note that Planck energy converted to Planck mass is really a lot of mass packed into a very small space. This is why black holes form. The mass is equivalent to about 1% the size of a mosquito. Although this sounds really small, it's really large in energy terms. In fact, this mass converted to energy is equivalent to the energy contained in a tank of gasoline or petrol in your car. When you pack that much energy or equivalent mass to a size as small as the Planck cube, you get a black hole. This is a pretty large amount of mass for such a small volume. Why is this the case? You have to
Bada
remember how
bing,
weak
bada
gravity
bang.
is.
You got a
It's the
black
weakest
hole.
force in the universe. It's
You just got to take this much mass and this much size. Boom, black hole. Instant formula.
Because it's so weak, we have to pack a lot of mass for the gravity to be strong enough to form a black hole within that volume. Now, some people have used the precision of the various constants to argue for fine-tuning. This is the claim that conditions which allow life in the universe lie within such a narrow razor's edge that any slight variation
All the constants happen to work out like that because reasons.
for large astronomical structures like solar systems or complex compounds
I didn't get what that
life as we
meant.
know it. And some argue that the chances
Definitely not God, dude. But what are the like? What a random chance. Are we lucky, bro?
entered into the program, or that a supernatural being, God,
Oh, there you
must
go.
have chosen the constants so that life could exist.
There we go.
Others counter this argument by saying that the universe isn't all that fine-tuned for life because, by all accounts, almost all the volume of the universe supports no life. There's only a limited number of planets and a limited number of solar systems that are within limited distances from their stars with specific combinations of compounds, namely carbon and water, that are conducive to life as we know it. But if you look at the vast number of planets available in the universe that nature has to work with, there's bound to be life on some of them. Or that the constants are but one variation in a vast multiverse of universes.
That's a lot of
And
bowls.
life in a different
Dude, look at how
form could
insane
exist
we
with a
are.
different set of
We look up
constants.
at the sky
None
and
of
we're
these
like,
claims is currently
you couldn't even
falsifiable.
exist as a human based on your periodicity. What?
Dude, the parallax angle of that star compared to when I know the sun is and how big I guess Venus is actually means that you're a bajillion miles away.
Patreon. If you like my videos, consider joining them.
That's
Shout out
enough
to you,
praise
boy.
done.
Yeah, that was
He's
a good
done.
video.
It was very good.
But yeah, once the rules have been established, you're welcome to play Dungeons and Dragons, man. You can even become a dungeon master. But should you choose to deviate from that and try to establish your own lore, you will be swiftly dealt with.
No lore for you. Yeah, not allowed. Dude, the first thing they threw up was this one, right? It was like, oh, well, actually, it didn't say it was the speed of light. It ended up being the speed of light through like a dramatic reveal, right? But we knew what it was beforehand. And it's like, oh, it turns out all the properties of the thing that you think is real is just determined by the properties of the thing that it is in. So, like, the background medium.
What a precarious position to be in.
The properties of the medium itself actually is what determines the speed of light. So what does that tell you? Is the speed of light relevant? Absolutely. Does it mean that light beam is traveling at a rate? Fuck no. Fuck no. This is a quantifiable rate of induction, testifiable metric, right? It's metric, it's used, it's real. They just told you that it was, if you're like, so like if you have an experiment and you're riding a light beam like a cowboy from the center of that light beam and you're riding yeehaw and you're going around the universe, then this is actually the max speed that anyone can go, especially if you're only relative from yourself or whatever. I can't actually make the light beam work, but I can give you the math that if you were on that light beam, how it would look. Einstein in a nutshell.
What it would look like from a null geodesic. Outstanding.
I really like that presentation, guys. Learned a lot about constants tonight.
So that was constants. Yep. That's about it. Short one tonight. Well, a short one compared to the double decker 302 with those slide decks.
I woke up this morning and I didn't have any coffee. Where can I go to get some? Is there a place? Do you know a guy who deals in coffee in large quantities? Perhaps let me lay out a situation for you. I'm a busy guy, right? I'm reading PDFs all the time and typing on the internet and whatnot, right?
Twitter trolling or whatever.
Yeah, I don't have time to go to the store. I don't have time to do anything. But if there was like a website I could go to and I could subscribe to, if I could just say, here's my money, you send me coffee on like a schedule. Is that a situation that could be arranged? Like, do you know anyone that can facilitate that?
Yeah, I do. I do actually know someone that. Well, actually, it's funny. It's funny that you should ask that because I happen to roast coffee, Alan.
What?
I don't know. Yeah, I don't know how
like that
you
gourmet
came
stuff
up with
or
that
what?
question, but yeah, I don't know, man. You seem to be. I don't know. There's some synchronicity going on, right? Because I happen to run a coffee roasting company called Brushtail Coffee. And it's me and a grill and a special drum contraption and I just I order beans from a couple of third parties and I work with different processing or they work with different processing facilities and I pick what I like and I roast it. And if you order coffee from Brushtail Coffee, it will be roasted to order. So you're not going to get coffee that's been sitting around or that's a certain batch from whatever day that I'm going to, throw into your shipment and ship it off to you. No, you'll notice I have multiple different types of coffee. And if you pick one and order it, it will be roasted to order and it will be shipped within the day, typically within 24 hours of when it was roasted. That's generally the latest it would go. And that way it will get to you within 4 or 5 days at the most. And that way you can have coffee within the week it was roasted. Sometimes sooner than that even. But in any case, coffee is definitely noticeably better within the first first 2 weeks essentially. And then it kind of starts to slowly taper off after that. If you buy your coffee at the grocery store and it has a best buy date, like an expiration date instead of a roasted on date, then you don't even know when it was roasted. And that's a totally different metric to date your coffee by. So if you want to try fresh coffee, head over to brushtailcoffee.com or brushtail.coffee, BRUSHTAIL .coffee. So yeah, thanks everybody.
That sounds too good to be true. I've heard a lot of these coffee companies allegedly could use baby penguins in their mixtures. Are you giving me
Mm.
assurance that your coffee doesn't use any baby penguins?
We've actually walked back our claim on that because you know, some legal issues. So there may or may not be, let's just,
Well, listen,
no one
guys,
really
we have a new marketing campaign. There was an issue going on, like Toby said. We were deceived by our marketing manager. That person's been let go. The new PR manager is about to release the new campaign based
The new
on
scapegoats here. I mean,
Yeah.
new marketing manager.
exactly exactly. So what we have here is I was watching an episode of Alex Jones, InfoWars, and he was saying that he read a study that if you drink coffee that isn't home brewed from Brushtail Coffee, it'll actually make you gay.
Oh, that has merit. I heard about the frogs. So
Good to know. Yeah,
Right.
that may or may not be, that's a superposition of truth. And yeah. So there you go. Wow.
That's good to know. That's science.
Yeah.
all
Well,
this talk about coffee made me thirsty. I literally had to go buy some Brushtail coffee. So
Yep. Brushtail
Wait,
Coffee.
Toby, are you saying there's no baby penguins in your coffee?
No. That's what I'm not
That's-
saying that anymore.
What? Okay, you know what? I'm gonna cancel my order. I thought I was getting
Fair.
ground baby penguins.
Oh
So
no, you
please
are. You are.
cancel my
No,
order.
Alan, no, she may or may not be.
Oh wait.
Just
yeah.
cancel
For legal
my
reasons.
order of 30 pounds.
Oh, today's opposite day. I see what you're doing, Lily. Thank you. We'll cancel that order right away. Toby's not
Yeah.
firing up the grill right now.
And pulling out the extra beaks.
dude, I ran out of coffee like 3 days ago, and I went to the store and I bought Maxwell, which is full of baby penguin beak, as far as I can tell from the taste and the texture. Now that I've been on Brushtail, so I immediately want to just throw up, and that's why I bought coffee just now. Anyway,
Yeah, I was looking at Folgers, and based on observation alone, I can see. I guess.
Jesus.
I
All
can
right, we're
tell
wrapping
the
up, lads.
baby-
Thanks for coming out. We'll see you
Yeah,
on
yeah,
Thursday
yeah.
for the community chill sesh on Twitter Spaces. Looking forward to it, lads. And then, of course, Friday will be Flat Earth Fridays. See you
Yeah,
there.
thanks for tuning in, everybody. Take care.